All right, the recording has started. This recording will be available in the announcements once I have put the video through captioning. It usually takes about 24 hours. So if you want to access the recording for any reason, give it about 24 hours and then it'll be available. Just to let those folk who weren't here last week know, there weren't any recordings from last week's meetings because we didn't have to meet because everybody was in the lecture class. And since this was an introduction, last week was an introduction to the course, um, all of the material that we dealt with in lecture was relevant for the material that you had to deal with in lab. In other words, the week one material was the same in both classes. So I didn't have to do, introductions in this particular class last week because I did it in lecture. All right. Um, so with that being said, what I want to do is open up the floor for questions. If you have a question regarding anything that you reviewed during last week's material, please just feel free to unmute and ask your question. All right, I'll take that to mean that all is well. And so I'm going to go ahead and share my screen. Okay. And so what you should be seeing now is the course homepage. Somebody please just unmute and let me know if in fact you are seeing the course homepage.
Yes.
Okay, great. All right. So what I'm going to do now is go into the weekly overviews. I get to the weekly overviews by clicking that link on the left menu. So you can see here, this is a breakdown from week to week of the topics that we'll be covering. So what I want to do today is I want to cover the material. I'll do the error analysis and graphing today. And then on Wednesday, I want to do the density overview and I'll talk about the project. Okay. So that way, two things today we'll talk about, two things on Wednesday we'll talk about. And that way we can, try to utilize the time that we have wisely, if you will. All right. So the first topic area that we need to deal with is error analysis. Okay. And so error analysis is built on the concept of measurement, because you'll see here in a moment when I cover some items for you that anytime you make a measurement, it involves, reading some type of scale, and so there's error. So those two topics kind of in a laboratory setting go together. In lecture class, one of the things we started talking about was measurement. And so the goal here is for you to use your understanding of measurement. And then once you make those measurements, you have to deal with the error associated with those measurements. So that's where we're going, okay, this week in terms of this topic, all right? And so we'll take a look at all of these items under activities here shortly. But I did want to bring to your attention before I do that, there is always some required, there's some materials available for you to review before you actually tackle the experiment. So there's some videos on measurement, some notes on percent error, so on and so forth. Let me be perfectly clear with you. In this particular class, we're focused on the experiments that we have to do. This is not a lecture class. So what I try to do is give you enough information to help you complete the experiments, do your lab report, so on and so forth. But I don't lecture on these, on the content, if you will. That is dealt with in lecture class. All right. So that's why I like to make material available to you, so that if you need to refer to it, you have it available. All right. Any questions on that? All right. I did fail to mention. I don't know if you can see this, but in the event you haven't done so already, please sign and return to me the last page of the syllabus. That was one thing you were supposed to do last week, and if you didn't get it done, I need you to go back, take a look at the syllabus in week 1, and sign the last page and date it and send it to me by email. Okay, that's a reminder. I forgot to do that before I jump right in. All right. So what I want to do now is I want to talk about this whole measurement and error. I'm going to explain the experiment. I'm going to explain the lab report and the discussion that you have to do. And then you can ask me questions about it. And then we'll go forward and do the same thing for the graphing material. Okay. All right. So what I'm doing now is I'm opening the measurement and error experiment handout. Again, the experiments are found in the weekly overviews. You will not find them if you don't go into the weekly overview. Okay. All right. So you can see here, there are some goals and objectives that I have for you doing this experiment. And I always tell you up front, what is the expectation? What kind of things should you be able to do as a result of completing this particular assignment? All right. So now what we have to do here is get an understanding of error and the role that it plays in the experimental process, in the laboratory process. All right. So when we talk about error in the laboratory setting, we don't mean the same thing as a mistake. All right. In everyday conversation, error and mistake are often taken synonymously, right? But not in a laboratory setting. Error and mistake do not mean the same thing when you're working in a lab. Okay. So error is referring to the uncertainty in a measurement. Okay. And anytime you're in a laboratory setting and you make measurements, even if you make measurements outside of the laboratory setting, anytime you make a measurement, these measurements have error associated with them. Okay. That is because no measured quantity can be determined with infinite precision. You cannot get infinite precision if you're using a finite measuring device. Okay. So let's be clear. In a laboratory setting, whenever you make measurements, you will have error. In a laboratory setting, when you make measurements, you need to eliminate the mistakes because they do not mean the same thing. Okay. We typically think of mistakes as the result of sloppy work or some carelessness, if you will. And that means, for example, you might misread a scale. Well, if you misread it, that's not an error. There's nothing wrong with the scale. That's a mistake, which can be eliminated. See, the difference is you can eliminate mistakes, but you can never totally eliminate error because it is part of the measurement process, because of the limitation in your measuring device. Okay. So, multiplying 2 times 3 and getting 8, that's just, that's a mistake. That's a math mistake. Okay. So you want to avoid those kinds of things, right? But you can't avoid error. You cannot. Okay. You cannot get rid of error, but what you can do is work in a way to minimize it or reduce it. And so in order to do that, you need to know what types of error you come across in a laboratory setting. Okay. And so one type of error is statistical error. Statistical error. Okay. Sometimes you'll hear it called random error. And that is because it's not predictable. There's no pattern to it. Okay. And so when you're dealing with statistical error, the challenge is that you have to use a measuring device that is not infinite. You are dealing with reading a scale of some sort, and that measuring instrument is limited. Okay. Even the width of the lines on the scale is not zero. They have some, thickness, if you will. All right. And so as a result, whenever you read a scale, you have to estimate the last digit of the measurement. And that estimation is what introduces the uncertainty. Because you could ask the question, well, did I estimate too much or did I estimate too little? Okay. And so, when you're doing this estimation, that type of estimation is random, because half of the time you might estimate too little and the other half of the time you might estimate too much. So the expectation is that if you make a large number of measurements, half of the time you'll estimate too much and half of the time you'll estimate too little, but that'll cancel each other out. So you measure multiple times, you do a large number of measurements, and so and you calculate an average, and then the estimation errors will cancel each other out. But here's the thing, for that to work, you'd have to do an infinite number of measurements. So you're not going to ever totally eliminate this random error because you can't do an infinite number of measurements. Okay. But you can reduce it by making multiple measurements of the same, quantity or property. And, when you do that, you reduce the amount of random or statistical error. Okay. And so it tells you here, make a large number of measurements. Well, that sounds good in theory, but the reality is in practice, we're only in this class for 8 weeks. You don't have time to measure the same thing over and over and over and over again. Or we'll never move beyond, the first experiment, right? You'll still be measuring stuff for experiment number 1 in week number 8 if we're trying to make a large number of measurements. So the reality is that for this class, or many times in a laboratory setting, you're forced to be content with a single measurement, because if you get to measure something once or twice in this class, that's a winner. And so how do you deal with that? If you have to make a large number of measurements to reduce the random error, but you can't make a large number of measurements, what then? Well, it tells you here in the handout, in the experiment handout, that the error estimate on a single scale reading can be taken as half of the scale width. So for example, if you're measuring length with a meter stick has the smallest scale division as the millimeter. And so if you use the meter stick once to make a measurement, the best you could do is plus or minus half a millimeter, plus or minus 0.5 millimeters. Okay. And so they give the example here that if you made a reading of a length using the meter stick and you quoted that as 17.0 millimeters plus or minus 0.5 millimeters. So the 17.0 millimeters represents the mean or the average, and the 0.5 millimeters represents the error on the mean or the error associated with that average. So what you're telling everybody is that all of your measurements fall within the range of 16.5 millimeters and 17.5 millimeters. Okay. So if you measure multiple times, then the error will go down. It'll be less than 0.5, but only if you only measure once, the best you can do is plus or minus half of the smallest scale division, which in this case is a millimeter. Okay. All right. And so they talk about here how you can find the error on the mean. Now, you need to understand this because when you do the project that I'm going to be talking about on Wednesday, some of you will come across data and you know, error analysis done on that data, and you'll see things being reported in this format. So you have to know, what does that mean when you see it in these research reports that you're going to be looking at. And so they're telling you the mean plus or minus the error on the mean. Now, I don't have you calculate it because honestly, we don't get to make multiple measurements of the same thing. And number two, well, I mean, I'm sure, you know, most of you could tackle this mathematically, but we have a simpler error analysis technique that we're going to be using, and I'll introduce it to you shortly. But it doesn't mean you don't need to understand this because you are working in a laboratory environment, okay? And you'll be coming in contact with research reports where they may be reporting their error in that format, all right? The other type of error that you come across in a laboratory environment is systematic error. Systematic error. Now, it's called systematic error because there's a system to it. There's a pattern to it, right? And you might think, well, hey, you know, there's a pattern to this error. So if we just identify the pattern, we can account for the error, right? The problem is that you don't know the pattern and you don't have any way of finding the pattern, because in this case, the pattern is hidden from you. It's, you know, difficult to detect. And so making a large number of measurements won't help you because those large number of measurements will all be systematically off, right? And this could be because you're not familiar with the instrument that you use. You know, you have no way of knowing if the instrument is functioning as it should. You're not familiar enough with the instrument, or you're not familiar with the reading that you're supposed to be getting. In other words, you have no idea, while I'm measuring this thing, what kind of, you know, value should I be getting? So if you're not familiar with the instrument and you don't know, you know, what values you should be getting from the measurement, that makes it very difficult to know if you're off, right? So you can't find the pattern. So what you have to do to deal with systematic error is to be mindful and calibrate your instruments, okay? So you want to, as we say in simple terms, you want to zero it out, right? I mean, in a high-speed lab setting, you would probably call a National Institute of Standards and make sure that your instrument is calibrated with, you know, according to the standard that they maintain. But, you know, we aren't calling them. I mean, so, you know, I always tell students, we're going to, you know, you zero out your instrument the best you can and you move forward, right? So that means you probably, you may have some systematic error in there, but that's just the nature of the beast that we deal with. But you do need to understand that, you know, what is systematic error and how would you deal with it in a laboratory setting, okay? Right? So, you know, you have to be mindful of the fact that, you know, in a laboratory setting, we don't say human error. Human error means mistake. And our goal is to eliminate mistakes. But we could have the best equipment in the world and we still have to account for error because no measuring instrument is going to be infinitely precise, right? So random error, you have to measure multiple times. Systematic error, you have to calibrate your instrument, all right? So if we aren't going to have to worry about measuring things over and over again, and we zero out our instruments the best we can do, then what kind of error analysis method are we actually going to use? How are we going to account for the error in our measurements? Well, you see, we have the good fortune in this class of dealing with properties and quantities of, we're dealing with things that we can measure where we know what the correct or accepted value is. In other words, we know what value we should be getting whenever we do our measurements, okay? And so because we are comparing our measured or experiment value to a known or accepted value, we can use what's called a percent error calculation, okay? So in a percent error calculation, you take your experimental value and you compare it to an accepted or standard value, okay? And here's the formula that we use for percent error. Percent error equals our standard value minus our experiment value minus our accepted value. And then you take the absolute value of that and you divide it by the accepted value, and then you multiply times 100, okay? So let me do something right quick that might help you out to see this formula a little clearer. And you have to tell me if you're seeing this on the screen once it comes up, because I've had the issue sometimes I had to stop share and reshare for it to come up, but let's see if you can follow. Okay, if this thing wants to come up. All right, can you see that? Can you see this whiteboard here? Somebody let me know.
Yes.
Okay, great. Okay, so I'm going to write out the formula, but I'm going to write it in a kind of a more I don't want to say simplistic, but I say a more reader friendly. So percent error equals, so okay, so experiment okay value, and I apologize, I'm not the greatest with the like whiteboard pen here because I'm doing this with a mouse. Oh, this, okay, minus okay divided by, oh, nope, okay, the right value times 100. I think that's a little bit more user friendly, if you will, in terms of seeing the formula written out. Okay, so because we know what the right value should be, we know what you should be getting, then you can compare what you get from your experiment to that right value. And the way you do it is you take your experiment value and subtract the right value. Some books will write the right value minus the experiment value. It doesn't matter which order you subtract because you have these absolute value bars. These absolute value bars, okay, so I'll write the absolute value. Somebody tell me, do you know what absolute value means? What does that mean? If you take the absolute value of something, what do you do? Feel free to unmute if you know. Okay, so what you do is you drop the negative, right? So it doesn't matter which order you subtract because you drop the negative. Oh, the absolute value bars tell you drop the negative sign. So if you subtract and you get a negative number, you drop the negative sign. So that means our percent error values for the things we're going to be dealing with, the percent error will come out positive. Percent error is positive. Okay. So if you're calculating and you get a negative value, you go back and reevaluate because the absolute value bars tell you drop the negative. Okay. All right. So any questions about this formula? What I'll do is, what I typically do is I screenshot these things and then I'll make this screen available to you on Canvas. Okay, so a lot of times what I do is I post these screens like this, the whiteboards, I post them in the announcements along with the recording. So you have access to this stuff when you're working. Okay, all right. So I'll say make that available to you here shortly. All right. So if you wanted to practice using the percent error formula, you could take these numbers where this is the accepted value means the right value, and then experimental results is the experiment value. And if you plug these numbers into the formula that I just put on the whiteboard and practice with it, you should get 2% error. If you are calculating and you don't get 2% error, then maybe you ask a question. So before we sign off for tonight, my suggestion to you is try it, and then if you don't get 2%, ask me a question to let's make sure we understand where you might be going wrong with that. Okay, so now you can see very clearly from the percent error formula that in order to use it, you have to have measurements, right? I mean, if you don't have any measurements, then you don't need to worry about error. But if you're making measurements, then you have to have a way to determine the amount of error. And our method for doing error analysis in this course is going to involve doing percent error. So you have multiple opportunities to practice doing percent error before you have to demonstrate to me on your final exam that you know how to do it. Okay? All right. So how are we going to get the measurements? So what I have you do is to measure some common items that you might find around your home. Okay? That's the thinking here, but just bear with me for a minute. I'm gonna get you there. Okay. So you could, well, put it this way. I have some sample data that I'm going to share with you, but the sample data was arrived by following this process. Okay. This portion of the handout is a description of the experimental process. All right. But for this one, because it involves actually measuring items that you might have around the home, and some of you might not have the measuring devices, I provided some sample data that you can use, and I'll share it with you momentarily. But let's just discuss the process of how you would arrive at that sample data. Okay. So I wanted you to utilize 3 cans from your pantry that are marked with volume units. Okay. And some examples of volume units are things like milliliters and liters and gallons and quarts. Okay. And fluid ounces. Those are examples of volume units that you might find on a can that contained a beverage or liquid. Okay. So like a can of Dr. Pepper or a can of baby formula. Um, those are examples of beverages that would have volume units. What I am not talking about is like a bottle of Coke, of soda, Coca-Cola. Okay, not a bottle, but a can. So the bottle will have volume units, but it's not something that's easily measured. So the cans are much easily measured. That's why I'm utilizing the cans. And for those cans of beverage that have volume units on them, you have to measure the height and the diameter. You measure the height of the can by, just measuring how tall a can is. And then you measure the diameter by measuring the distance across. So you measure the height and diameter if the can has liquid contents. Okay. And once you measure the height and diameter, then you need to utilize this formula. Okay. Now, the formula requires that you use the radius. The way you get the radius is to take half of the diameter. Okay. The reason I have you measure the diameter is because that's a much cleaner measurement. Okay. So once you have the diameter, take half of it and plug into this formula. Pi, which is 3.14, times the radius again, times the height. In other words, the volume formula is pi r squared h. And so then once you measured your can of beverage, you will, and I tell you the measurement has to be in centimeters. When you plug those measurements into the formula, you get the volume in cubic centimeters. Sometimes you see that as cc, cubic centimeters. Okay. So you'll do that for 3 cans of beverage. And I always tell students, if you're going to do this, you can't pick all of your cans the same. Not a can of Dr. Pepper, a can of Sprite, and the cans are the same size. Then you're going to have the same measurement over, you're going to have the same measurement for those 2 different items. But what you would typically want are cans of beverage that are different sizes, right? And so once you have measured those values for those 3 items, you've used the formula to calculate the cubic centimeters volume or the length volume for those 3 items. Then you're going to plug those values into the percent error formula. Well, you're going to plug in the value that you calculate from the volume formula and the value that's on the label. Okay. And see, I tell you what, use the percent error formula to find out how close you are to the accepted milliliter value. The accepted value is the milliliters on the label. So you measured in centimeters, you calculated volume in cubic centimeters, and now you're comparing that to the milliliters on the label. Why? Because the label will not have cubic centimeters. It will have milliliters. And I tell you how you convert your cubic centimeters to milliliter. 1 cubic centimeter equals 1 milliliter. 1,000 milliliters equal 1 liter. So these are some conversion factors that you will use in this experiment. And we're going to talk about conversion factors, volume units. We're going to talk about that in Wednesday's lecture class. But, you know, if you want to make the attempt of going ahead and working on this experiment, feel free. Because some of you probably understand some of this measurement business already. But if you don't, please ask questions, okay? So let me ask, for the volume items in this experiment, what are your questions about the process that you have to follow? Okay. Then you have to repeat this process, this percent error process, for some items that are measured using, that are mass units, okay? And so it says you need some cans of food with mass units on them. I put favorite beverage here. Honestly, unless your favorite beverage is mayonnaise or something like that, you want solid food cans, right? Things like corn and beans, solid food items you will need to do the mass measurement, right? So you measure the mass of the can in grams, and it says if you can only measure in ounces, be sure to convert your ounces to grams. This is why I gave the sample data, so you don't have to worry about that, okay? But by all means, if you have access to measuring the actual food cans, please feel free to do so, especially if you don't want to use my sample data, but instead you want to make your own measurements. That is perfectly fine, okay? So you're gonna take 3 cans with solid food items, and you're gonna measure the mass of those cans in grams. And then you're gonna use the percent error formula to compare that to the grams that are on the label, okay? And the reason we're dealing with the grams is because we focus on the metric system in this class, like, you know, as well as in lecture class, okay? So any questions about what you have to do to get the mass data for this experiment?
So basically, you're going from the other two to get the mass. I'm just trying to make sure I'm understanding.
You have to have 3 different cans,
Okay.
and those cans have to have solid food items. So in the volume part, you have to use liquids. In the mass part, you have to use cans of solid food, like corn, beans, that kind of thing. So you'd have to have 3 different cans, and you measure the mass of each of those cans. And then once you measure the mass of each of those cans in grams, then you have to put your values in the percent error formula, right? What did you measure versus what is on the label? What you measured is your experiment value, and the value on the label is your right value. That makes sense?
Yeah, I think I got it. If I have any other questions, I'll just email you.
Yeah, no problem. Please do so. All right. So
Oh wait, I'm
that's,
sorry. I
yeah,
do have one more question. I'm sorry.
yes.
Can we use this example? Because I know we have to write a lab on this. Can we use this example or no?
I'm going to talk to you about what you use
Okay.
in just a moment. Okay. So what I've described for you just now is the experimental process that you would go to collect your data. Okay. So What I allow students to do and what I will allow you to do is to use my sample data. Okay. So if you don't have a way to measure your own items, you can use my sample data. Or if you have a way to measure your own items and you don't want to use my sample data, measure your own items. But you're more than welcome to use my sample data here. Okay. Right? So what I did was I gave you 3 mass items. Notice these are all solid food items. And I told you what is the value in grams on the label and what is the value that was measured for these 3 mass items. So if you followed that experimental process in the mass section of the experiment handout, you would arrive at this mass data. So rather than making your own measurements, you can use mine. If you don't like my measurements, measure your own items. Okay. And
Um,
below, yes.
I'm sorry. I'm trying to. I had a question.
Yeah, go
Just
ahead.
um, and this is the measurement in error, right, for the lab, correct? I'm just making sure I'm.
What do you mean? Is this the measurement in error?
This is the assignment for the measurement in error, correct?
Yeah, that's the overview that I'm in.
Okay, and for this one, I'll just wait till you're done, and I'll just ask questions at the end. I'm sorry.
Okay. No problem. You can ask your questions anytime you have them.
I'm just trying to make sure I'm just trying to take notes at the
So
same time.
are you following along on the screen?
Yes, I'm following along. I'm just trying to write notes at the same time and do this. That's why I was just asking
Okay.
for the lab for the just trying to make sure I'm doing this right. So I know on here for the assignment you want us, if it's typed, we have to email it to you. So this is for this one for
I haven't got to that part. Right now what I'm explaining is the sample data, right? So I went through the experiment and explained how you would get the data. Now I'm sharing with you an example of data that was collected following that experiment process. What I have not talked about yet is writing the lab report. I will get to that in a moment.
okay.
Yeah. So now back to the sample data. So I discussed the idea of the mass data. These are 3 mass items. This is what was on the label of those 3 items. And this is the value that was measured when these items were put on the scale. Okay. Below that, I have volume data. So if you follow the experiment handout and went through the process that I described of measuring the height and diameter of those liquid canned items, then here are 3 liquid canned items. Here is the height of each one of those items. Here is the diameter of each of those items. Here is what was on the label in milliliters, right? So I'm the height in centimeters, the diameter in centimeters, and the label value in milliliters for each of these sample items. And these measurements were made by following the process that I discussed in the experiment handout. Okay. So you are more than welcome to use my sample data for your volume and for your mass if you choose to. All right. So imagine that you went through the process that I described here in this experiment handout. And after you completed that process, this was the data that you came up with. And if you don't like my data, you can definitely measure your own 3 cans of liquid items and 3 cans of solid food items. All right. So, so I've discussed how you do the experiment. I've discussed the data that comes out of the experiment, whether it's mine or yours. And now what I want to discuss is the lab report that you have to write. Okay. So what I've given you here in this handout, Now notice the way I got to this handout is I'm in the weekly overviews under activities, and there's the experiment, there's the sample data, and then there's a link that says what goes in the lab report, measurement and error. So I am guiding you to what do you need to do to write your first lab report, okay? So the goal here is for you to write your first lab report. Here's the title, here's the report format. This is the title of your first lab report, measurement and error. Then you need to put your name, and then you're gonna write me an abstract, okay? Now in that abstract, you have to give enough information so that anybody who wants to repeat this experiment could take your abstract, follow it, and come up with the same, they could reproduce the experiment. So you have to put enough detail there, right? So what you need to do is you need to explain exactly what you did, explain the procedure that you followed. And in this particular case, you should envision the procedure that you would follow. Well, not envision, you should explain the procedure that you followed to get the sample data, if you're using my sample data. And if you're using your own data, explain the procedure that you followed to get your own data. What did you measure? What tools did you use? What formulas did you use? Okay, so you have to explain all of that in the what you did section, how you did it. Well, if you used a meter stick or you used a scale of some sort, explain what tools you use and what measurements you made with those tools, okay? And right here it says the simulator used. You're not using a simulator here, so that's not relevant, okay? Why you did it. What was the whole goal of doing this experiment? Why did you do all those measurements in the first place? What were you trying to understand? Okay, and then what you found. So discuss the quality of your data based on the size of the percent error values. Okay, don't worry about the simulator part because you didn't have a simulator. But in this particular experiment, you're calculating percent error. So you should explain to me how good you think your measurements are or your calculations are based on the size of your percent error values. So for example, if you calculate percent error and you get 10% error, you might say to me, I think, given the instruments that I used and the data values that I found, this was a very good experiment because my percent error was relatively low at 10%. You might say, well, based on the data that I collected and the calculations that I did, this was not a very good experiment because my percent error values were 10%. In other words, I do not tell you a cutoff value for saying if you got anything below this amount, you did a good experiment. If you got anything above this amount, you did a poor experiment. I let you as the experimenter decide whether you think the experiment was a quality experiment or not based on your percent error values. You make the call, right? I don't give bonus points if you got a small percent error, and I don't take off points if you got a large percent error. I will take off points if you don't do a percent error calculation, or I will take off points if your percent error calculation is wrong based on your numbers, okay? So when you write me an abstract, you have to write sufficient detail to answer these 4 questions. What did you do? How did you do it? Why you did it? And what you found in terms of, the quality of the work, okay? Any questions about the abstract part of this lab report? Because that's typically where students, kind of miss some points because they don't give us sufficient detail. All right. After you've completed these first 3 steps, the title, your name, and the abstract, then you want to go and fill out this table or create your own table following this format. Follow the layout below. So even if you write it on a sheet of paper, it should be laid out just like this, where you fill in the name of your item, the height in centimeters, the diameter, the radius, which is calculated by taking half of the diameter, and then the volume calculation following this formula, pi r squared h, and your unit is centimeters cubed, and you have to show all of your work in the table, okay? So sometimes students will show where they took the formula and filled in their numbers and give the answer. Sometimes they'll go step by step, and you know, for each part of the calculation, you have to show me your work on how you got the volume data, volume value, because I need to know that you know how to calculate volume. Why? Because it's a derived property that we talk about in lecture. In lab, I want to see that you can actually do it. Okay? So this is your volume data, and it should be organized just like this. Okay? Below the volume data, you're going to fill in the table for the mass data. And it says, follow the layout below, make your own measurements, or use the sample data. The item name and the mass in grams. That's your mass data. Okay? If you're using my sample data, you simply pull it, you know, copy it down from there. Or if you made your own measurements, list the items that you used and the mass that you got in grams. Remember, volume items are liquid, mass items are solid. Do not mix them up. Okay? So what are your questions about the volume data portion or the mass data portion of the lab report? All right. After that, you do the volume analysis. And so again, you will write down the item name. You will write down the value of milliliters that's on the label. You will write down your volume value in milliliters. But since you did not calculate your volume value in milliliters, you calculated your volume value in centimeters cubed, you have to include this conversion factor to tell everybody, hey, this is how I got my volume values in milliliters. Every centimeter cube is equal to a milliliter. So up here, if you got 575 centimeters cubed, that's equal to 575 milliliters. Okay? But you're doing this calculation in milliliters because you have to have milliliters for your volume because the label is in milliliters. And you can't do milliliters and centimeters cubed. So you have to make sure the unit is like, right? So once you have your label values and your volume values listed, then do a percent error calculation, okay? And I tell you exactly, to get the percent error, you take the absolute value of the label minus your value divided by the label times 100, or in other words, this formula, okay? Once you've done that for your volume values, then you'll do it for the mass values. The item name, the value in grams that's on the label, your mass that you measured in grams, and then a percent error calculation for each. Please show all steps in the table. If you do not do the work in the table, I will take off points because you are told to follow my layout, okay? Any question about the volume or mass analysis that you have to do? Okay, after you've done your analysis portion of the lab report, then write me a conclusion. Now, granted, under normal circumstance, a conclusion, you would be explaining something that you learned from the work here, whatever. I mean, some conclusion that you can draw from the work that you've done here. But in my conclusion, and if you looked at the lab report format that you were supposed to last week, it tells you that when you write a conclusion for me, you are to explain what you learned. So please explain what you learned, not what you did. Okay? All right? Do not tell me about steps. Do not tell me about theory. Tell me what you learned. Explain a concept, skill, tool, or formula that you learned as a result of doing this experiment. And in this one, tell me why you never got 0% error. If you did your calculations correctly, nobody will get 0% error. And I want to see if you're thinking well enough to explain to me why you didn't get 0% error. Okay? So that's your very first lab report that you have to do on error analysis. So what are your questions on the actual lab report? All right. So for error analysis, we took a look at the experiment. Well, we took a look at the different types of error. We talked about how you can reduce the error, how you calculate percent error. And we looked at the experimental process that you have to follow to get the sample data or your own data. We talked about the lab report that you have to write. And below, it explains to you how to submit the lab report. If you type it out, just email me the Word document or, whatever format you type it in, right? If you write out your lab report, you can scan it or take a picture of it. Make sure that your name is in the subject line and you put the course number as well. And then you can email it to me. And then these are the formats that you're allowed to use: PDF, Word, and picture formats. Please do not send me Mac pages because I cannot open that. Okay. So that's how you submit the lab report to me. And again, if you're looking for all of that, it's right there in the weekly overview. Okay. So after you've done the experiment, after you've written your lab report, then you're going to do this post-lab discussion. And so this discussion deals with concepts that were covered in the experiment or in the lab report. And so you answer the questions first, and then you have to comment to 2 of your classmates regarding their posting. You should try to have a conversation with your classmates about their posting. Things like, I like your answers, or we got the same thing. That doesn't further the conversation. What you want to do is, ask questions. Well, how'd you get that answer? Or, hey, I got something different from you. Or we got the same answer, but it looked like we did it a different way. Or, hey, did you think about this aspect of it as well? So just like if you were face-to-face talking with each other about how to answer these questions, or, sharing with each other while you're working and answering the questions. So it's meant to promote discussion, right? And so these simple 3-4 word answers will not suffice. You will lose points if you do that, okay? That was fine for last week's stuff because it was just you introducing yourself. But now we're getting to the actual work. I expect that you will, try to have a deeper discussion with your classmates about these questions and their answers as well as yours. Any questions on what you do for the discussion? All right. The only other thing that I want to show you in this overview is that if at any point you want to drop a line in the class questions forum, I'm conditioning myself to take a look at this each day. And if you put a question out there, I will answer it if you're, looking at it and you want to chime in and post an answer, it's just another avenue for us to have, communication. All right. So, any questions about the error analysis overview in terms of the activities that you have to complete by Saturday? All right. The next experiment that I want to get into is the graphing experiment. So of course, there are multiple objectives here. What I will say to you is, in a nutshell, what we're trying to do in this particular overview and through these particular activities is to teach you how to do a proper scientific graph, because the level of detail that you have to engage in for a proper scientific graph is much different than like the graphs you might do in a math class, for example. Okay. I've provided some resources for you. There's some practice that you can try on this simulator. There's some videos that talk about graphing as well as best fit lines. So you can utilize these resources to help you as you're working through, the experiment, lab report, so on and so forth. Okay. So what I'm going to do is I'm going to explain the experiment, talk about what you do in the lab report, and then the post lab, so on and so forth. Okay. All right. So in this particular experiment, the goal is to get you to understand graphing. Okay. And so what you have to do is you have to click on this link and go out to this website. All right. So I'm going to have both of these open and I'll flip flop between the two of them. So this is the website that you're going to utilize to do the graphing experiment. Okay. What you have to do, this is the experiment handout. What you have to do is you have to read and follow all of the instructions provided on that graphing website, except you don't have to take a quiz. Okay. All right. So when you come to this website, when you open this website, you can see just by scrolling through, there are 7 parts to this website. Okay. You are going to work through each part of it, except you don't have to worry about any quiz. You see, because it says there about a lab quiz. Don't worry about that. Okay. So you go through, come to part 1, you read all of the parts of part 1 where they describe for you the idea of a graph having an independent and dependent variable, how you plot numbers on a graph, so on and so forth. Okay, you're going to work through this. When you finish part 1, then you go to part 2. Okay. Part 3 discusses the equipment and supplies that you need. Of course, my rule is that you do not use graphing software. You must do your graphs on graph paper. So you can go to the store and get you like a, $1.50 pack of graph paper and utilize that to draw your graphs. Okay. There are lots of graphing websites, but because this is a learning activity, I want to see, at least for this experiment, that you're able to produce the graphs on graph paper, because then if you can do that, then typically you don't have problem using graphing software because you know what you're doing, right? Okay. So, a nice sharp pencil, a straight edge for drawing straight lines, a calculator because you're going to be calculating some things to put on the graph, and then the graph paper, right? And then when you get to step 4, there you start the procedure, okay? And so what you have to do in this step in part 4 is you complete this table, and they tell you how to get the numbers that you put in the table. They tell you that, okay? And then you graph that, okay? And look, they even got a place where you can print graph paper if you wanted to do that. Step number 3, the next part, they're telling you to do some things with the graph. In this particular case, calculate the slope, so on and so forth, okay? Then you get to another table that you have to complete. They explain to you how to complete the table. Then you graph that table. And then so on and so forth. When you finish the first 6 steps, you will have 4 tables and 4 graphs. When you complete steps 1 through 6, you will have 4 tables and 4 graphs. And then in section 7, there are a series of questions that you have to answer. So when you finish this entire experiment, you will have 4 tables and 4 graphs and the answers to the questions in section 7. Okay? Below this information, I have given you some additional information that might be helpful to you. You can read through it. A lot of this information is also represented on the website, but it's just, you know, I kind of pulled it out of the website and put it all in one place for you, okay? So that's the experiment on graphing. Go to the website, work through all 7 sections. You will have 4 tables, 4 graphs, and the answers to the questions in section 7. What goes in your lab report? Let's take a look. For lab report number 2, graphing, read and follow all instructions and information provided in the experiment handout. Complete all required activities and answer all the questions. When you are finished, you should have 4 tables, 4 graphs, 1 for each table, and the answers to the questions in section 7. This complete packet is to be turned in lieu of the standard lab report. In other words, you don't have to write a lab report. All you have to send to me for this experiment, for this lab report, send me your 4 tables, your 4 graphs, and your answers to the questions in section 7. Okay? That's what you turn in for this graphing activity. All right? And then you're going to do a discussion where you answer the questions and then you respond to 2 of your classmates. Instructions on how you submit the lab report are there, but basically you're emailing me your items, right? That's how you submit things, right? And then if you have a question, you can drop a line in the class questions form. So, you know, again, activities and assignments, you do the experiment, you write the lab report, do the post lab, okay? And then I made reference materials available to you in the event you have additional questions. But of course, you can always reach out to me. You can drop a line in the class questions forum if you're working, and I'll be more than happy to reach out to you, okay? On Wednesday, I'm gonna talk about the project and I'm gonna talk about the mass volume and density experiment. What are your questions on the graphing overview?
Can you show me how to get to the website again?
If you open the experiment handout, there's the link.
All right. And then on the website, you want us just to basically do everything but the quiz, correct?
Right, everything except you don't have to take a quiz.
And for that, to turn in that, how do you want us to write everything down, or does the website automatically turn everything into you?
No, it does not. Because you're gonna complete the tables and you're gonna draw graphs on graph paper. So
okay, so basically
you have to email.
Okay, so basically the website is just for us to answer the questions, to do our graphs in our table, correct?
Yeah, the website is, you follow the information provided on the website so that you can complete the tables and make the graphs and then answer the questions, right?
Okay,
So
I'm just trying to make sure I'm just doing everything correctly. That's it.
that's no problem. Better to be safe than sorry, right?
Yes, I agree. Okay, so website, use that website for the graphs and the table. And then the graph and post lab discussion session, that's where we just discuss. And
There
then
are
the lab
questions,
report.
there are questions there that you answer, and then you have to respond to two of your classmates.
And then the lab report submission instructions. That's just basically us submitting everything to you.
That's just explaining to you how you turn it in.
Okay. Alrighty.
Okay. So at any point, if you're working, don't hesitate to reach out to me. I'm more than happy to answer any questions that you have. You have between now and Wednesday, right? So Wednesday, I'll open up the floor when we first start. And if you have questions about the measurement and error or graphing, you can ask them then. You can ask your questions at any point, but if you have them then, you can ask them then, and then we'll move on into the new material. The most important thing is if you have a question, please ask it, because typically I find that when students don't ask questions, that's when they make mistakes. So
I think I'm I think I think I fully understand everything that you want. Like, I think the only thing, if I have any questions or anything, I'll definitely email you.
Yeah, no
I think I'm
problem.
pretty
No,
I
no
think I'm
problem.
pretty good as of right now because I started on some of the assignments as we were doing some of the stuff like you were showing. I
All
just
right.
wanted to make sure I had like the understanding of all the directions that you wanted.
Not a problem at all. I appreciate you being diligent and asking the questions, because believe
Thank
it or
you.
not, you are helping your fellow classmates.
Yeah, I, I I think I'm trying to be a big help to myself and others.
You're doing an excellent job. So keep the questions coming. I don't mind answering at all. So we'll get back together on Wednesday and take a look at the project and the density experiment that you have for this week. And, and then we'll just keep chugging away at it. And, each week we'll approach it just like this.
Okay.
All right. Thanks for joining in tonight. So, shy of any additional questions, we're done for tonight. I'll see you back here on Wednesday.
Thank you. You have a nice night.
You do the same.